find the general solution in parametric vector form. If infinitely many solutions exist, find a particular solution. So we have this beautiful augmented matrix, and looking at it, we are delighted and excited because we realize this is almost in row-reduced echelon form. We can see the first pivot in the first row, all zeros below it, check. Moving on to the second pivot position, we see it's the only non-zero pivot in its column, hip hip hooray. And we move to our third pivot. Notice we skipped the third column and the fourth column. We're now in the fifth column, which is fine. So this is our third pivot, and it does have an entry above it. So we got to remove that using those three basic operations. So we want to row reduce the augmented matrix to row reduced echelon form. And this is this same solving algorithm. So again, thinking about our pivot here, our third pivot position. What do we need to do to this third row to eliminate the -4 in the first row? Well, we can replace it. We can multiply the third row by 4 and add this to the first row to attain the new and reduced first row. So this is going to leave us with the equivalent augmented matrix. So notice row 3, we have all zeros here. So even though we're multiplying by 4, it doesn't affect the first 4 entries of row 1. So we still have 1, 0, -8, 0. And then 4 plus -4 is 0. And 0 plus 3 is 3. And the remaining rows remain as they are. 0, 1, 2, -1, 0, 5, and 0, 0, 0, 0, 1, 0. And then we have a row of zeros. 0, 0, 0, 0, 0, 0. And we incorporate our dotted line to indicate this is an augmented matrix. And now we're really excited because we realize, hey, this is row reduced echelon form. And we're ready to think about what is this system telling us. So in order to determine what the system is telling us and to describe our solution set, we want to think about each row. What is each row telling you here? So we are moving across our first row. So we can see the first row is 1 times x sub 1. We have no x sub 2. Then minus 8 times x sub 3. We have no x sub 4, no x sub 5, and that is equal to 3. What about the second row? So we now want to move across the second row to think about what is this augmented matrix telling us? Well, we have no x sub 1s. We do have an x sub 2. We have 1 times x sub 2. We have 2 times x sub 3. We have minus 1 times x sub 4, so minus x sub 4, no x sub 5, and this is equal to 5. And similarly, we want to move across the third row here to think, what is this row telling us? Well, we have no x sub 1, no x sub 2, no x sub 3, no x sub 4. We do, though, have an x sub 5. We have 1 times x sub 5, or excuse me, yes, 1 times x sub 5, and it's equal to 0. And the fourth row is all 0, so we don't need to consider it. So what are your basic variables? Well, where are those pivot positions? The first column, the second column, and the fifth column. So these are our basic variables, and now the remaining variables are the free variables. So let's simplify this and rewrite this. Solving for the basic variables, I have x sub 1 is equal to 3 plus 8 times x sub 3. Solving for x sub 2, we have x sub 2 is equal to 5 minus 2 times x sub 3 plus x sub 4. We know x sub 3 is free. We know x sub 4 is free. And x sub 5 is 0. So here is our solution set in its linear equation form. So we want to take this and convert it to its parametric description. Giving a little more room. So we want a parametric vector for the general solution. What dimension is our solution vector in? How many entries does this vector have? 1, 2, 3, 4, 5. So we can say that our solution vector x is in R5, so we have an entry for x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. And now we're going to start here by simply writing what we found in the linear equation form of our solution. So x sub 1, we know, of course, is equal to 3 plus 8x sub 3. So I have 3 plus 8 times x sub 3. X sub 2 is equal to 5 minus 2x sub 3 plus x sub 4. So I have 5 minus 2x sub 3 plus x sub 4. X sub 3 is free. So looking, where are those other x sub 3 variables? They're right in the middle, so that's where I'll put my x sub 3. We know x sub 4 is free. So for that entry, again, we line it up with the other x sub 4s. And then x sub 5 in this case is just 0. So we're going to line that up with the constant column. Now, I think that sometimes this can be a little bit confusing when you first start. If you see it, by all means, go for it. Otherwise, it can be helpful to fill in these missing places with zeros. So anywhere you're missing an entry, add a 0 to remind you that there is going to be a 0 there. So there we go. We have filled in all of those missing entries with zeros, and we're ready now to break this up into 3 separate columns. Can you see those columns? We need a column for the constants. We need a column for x sub 3. And we need a column for x sub 4. So here we go, breaking this up. The notation for our final answer will have 3 columns. We have the constant column, 3, 5, 0, 0, 0. And I'll do this in 2 parts again just because we're just seeing this together for the first time. We then have the x sub 3 column. This is 8 times x sub 3 minus 2 times x sub 3, 0, 0, plus the column for the x sub 4. So that's going to be 0, x sub 4, 0, x sub 4, 0. Such that x sub 3 and x sub 4 are your scalars. Now again, we don't want to leave those scalars in the column vectors. We want to pull them out. So we have vector x. We have that same constant vector, 3, 5, 0, 0, 0. Pulling that scalar multiple of x sub 3 out of the second column vector, we're left with x sub 3 multiplied by the column vector 8, negative 2, 1, 0, 0. And last but not least, pulling that scalar multiple of x sub 4 out of the third column vector, we're left with the x sub 4 multiplied by the column vector 0, 1, 0, 1, 0. And again, this is such that x sub 3 and x sub 4 are free. They are our scalar values. So this is our final answer for the parametric vector form of our general solution vector. And again, remember that this is indicating to us the infinitely many solutions that exist depending on the values of the free variables, because they could be any scalar our little heart's desire. So how many solutions does this have? Infinitely many. So since there are infinitely many solutions to this system, let's go ahead and find one of those solutions. So to find a particular solution, you need to choose a value for the free variables. And being a lazy mathematician, let's go ahead, and I keep saying lazy, but it's just the most efficient and effective way to find a particular solution, not necessarily lazy. Let's let x sub 3 be equal to 0, and let's go ahead and let x sub 4 be equal to 0. So letting our two free variables be 0, a particular solution will be that constant vector 3, 5, 0, 0, 0 plus 0 for x sub 3 multiplied by the column vector 8, negative 2, 1, 0, 0 plus 0 multiplied by that, or letting x sub 4 be 0, we multiplied by the column vector 0, 1, 0, 1, 0. And we know that a vector times a scalar multiple of 0 goes to the 0 vector both times. Woohoo! So we can say, therefore, vector x, one particular solution to this system, is the constant vector 3, 5, 0, 0, 0. So we've gone through this case with this particular solution twice now. So hopefully you're starting to realize this is a nice quick way to find a particular solution to a system. And you can even see that particular solution without having to do any math. So here you have it. These are our final answers. We have infinitely many solutions to the system defined as this parametric vector. And this is just one possible solution to our system.